Welcome all. Welcome to this course on representation theory of general linear Lie algebra, GLN of C. So we will begin with the definition of Lie algebras and some basic examples. Later we will move to the basic definitions and more examples of Lie algebras. So after that we will only focus on GLN of C and its representation theory. So what is a Lie algebra? So Lie algebra is a vector space So a Lie algebra, so let's denote it by G, is a vector space over C equipped with an Lie bracket. Equipped with a Lie bracket, which is denoted by the bracket from G cross G to G. So this map satisfies the following conditions. So satisfying the following conditions. So first of all, this map must be bilinear in each variable. So what this means, so the Lie bracket is C bilinear map. So that means whenever you take these scalars for a comma b in C and x comma y comma z in G, we have, so let's look at how it acts on this elements ax plus by and then take bracket with z. So then it is linear in the first variable. So that means, so this gives a times xz plus b times yz. So this is what linearity in the first variable means. Similarly, we also have linearity in the second variable. If you take bracket x and ay plus bz, so then we get a times xy plus b times xz, and this should be true for all scalars a b and x y z in G. So this bracket must be a C bilinear map, and it also satisfies two more conditions. So first one is the skew symmetric. The skew symmetric says whenever we take a bracket with some element of G with itself, so the bracket xx, that should be 0 for all x in G. And the last condition, which is more important condition, so which is called the Jacobi identity. The Jacobi identity says whenever we take three elements from the Lie algebra G, so then if we compute these elements, the bracket xyz plus the bracket yzx plus zxy, so this addition of these three elements must be 0. So one way to remember this, okay, basically what we are doing, we have taken these three elements x, y, z and we have cyclically permuted them to get other elements. So the first element actually corresponds to x, y, z. So now if we just cyclically permute this, so then this corresponds to x, y, z, then this corresponds to y, z, x. So reading from y, z, x, then this corresponds to zxy. So if we take product of these respective elements, so then if we add them, then we should get 0. So that is what Jacobi identity says. So a Lie algebra over complex numbers is a vector space G with this Lie bracket satisfying these three conditions. So the bracket should be a C bilinear map, and it should satisfy skew symmetric and Jacobi identity. So, in this course, we will only deal with the Lie algebras and its representations over complex numbers. So, throughout the course, we assume that our base field will be complex numbers. Okay. So, our base field assumed to be complex numbers. So, we can also work over any algebraically closed field of characteristic 0, but for to simplify our life, we can just assume that that field is complex numbers. So, if we take this skew symmetric and Jacobi identity, we can easily see that that can be replaced by the following conditions. So, for example, skew symmetric is equivalent to the following condition. Whenever we take the bracket xy, then that must be same as minus yx, and this should be true for all x, y and g. Okay, let's prove this. So, what is the proof? So, let's say that skew symmetric implies this condition. So, let's call this condition 1. Okay. So, this condition, for example, like if we compute x plus y for x, y in G, then we get the bracket x plus y comma x plus y, that must be 0 using the skew symmetric, So, that means if we just use the bilinearity and then write it down explicitly, then you can see that this gives exactly the bracket xx plus the bracket xy plus the bracket yx, the plus bracket yy. But using the skew symmetric, we know that, so this element is 0 and this element is 0. So, that means this element being 0 implies this identity 1. So, this implies the bracket xy is equal to the bracket minus yx. So, 1 is proved. Now, for the converse part, if we take, okay, for the converse, if we take this x equal to y, then 1 implies the bracket xx is same as minus the bracket xx. So, that implies twice xx is 0. But the thing is, we are working over characteristic 0 field, so that implies that the bracket xx is 0, and this is true for all x in G. So, that means skew symmetric can be replaced by this condition 1. Whenever we take multiplication of x and y, then that is same as minus of the multiplication yx. Okay. So, this is somewhat important later when we introduce further notions like ideals and so on. So, now let us see how one can actually rewrite the Jacobi identity. The Jacobi identity, like I said, one way to remember this, take this cyclic permutation of x, y, z and then sum it over them. Okay. So, if I take x, y, z, so then with this x, y, z, so we can see that with this we have this element x comma y, z. So, now if we just cyclically permutate, then this will be permuted as y, z, y and x. Sorry, z goes here. Yeah, this must be y and this is x. So, this is z, x and y. So, then this corresponds to the element y, z and x. Okay. So, x corresponds to, okay, this is not the permutation that I wanted. So if we just rewrite, maybe let us write it in the word notation. This is x, y, z. Then this will become y, z, x. So then y, z, x. So that is the correct word, and then z, x, y. So this corresponds to z, x, y. So addition of these three things must be 0. So that is why one remembers the Jacobi identity. So now one can actually rewrite this using what is called add x maps. Okay. So given x in G, one can define what is called add x of add x map. So add x is a map from G to G defined to be y goes to the bracket xy. So note that the bracket is being C linear in both variables. So this map add x is actually C linear. So add x is a C linear map. So in particularly we have what is called this add map from G to this endomorphism of G. So which is given by x goes to add x. So we will later study this map. So indeed we will actually see that this is a representation of G inside this endomorphism of G. So this map add x, which is given by y goes to bracket xy, if we use this map, then one can see that this Jacobi identity can be rewritten as follows. So if we rewrite this, the bracket yz is equal to the bracket xyz plus the bracket yxz. So I will leave it as exercise to see that these two versions of Jacobi identities are same. Okay, the bracket xyz is equal to the bracket xyz and bracket yxz. Indeed, if you think about it, so this term corresponds to this term, and then this term actually corresponds to this term. Okay, so now how one can actually rewrite this for the adjoint add x maps. So if we think about it, all we are doing here is that we are applying add x on bracket yz. So in particularly, this is nothing but add x of the bracket yz. Okay, so this is exactly equal to, so this is just add x of y bracket z plus the bracket y add x of z. And you may wonder like what is the advantage of rewriting like this. And if you think about it, if you broadly actually think this Lie bracket as a multiplication defined on the vector space. Multiplication by definition it is just a C bilinear map from G cross G to G. So then you can see that this add x is nothing but derivation on this Lie algebra G. So basically add x of bracket yz satisfies what is called this Leibniz rule. So from this one can easily see that, so this is indeed a derivation of the Lie algebra G. Okay. So for any vector space A, okay, let us say A is a vector space equipped with a multiplication, equipped with a multiplication. Okay, let's call that multiplication A comma B goes to AB. So then a derivation of this capital A is a C linear map which is defined from A to A such that whenever you apply delta on AB, the product AB, then this delta should satisfy the Leibniz rule, which says this delta of AB equal to A times delta of B plus delta A times B. Okay, and this should be true for all AB and B. So that is what derivation means. Okay. If we take this definition of derivation for general vector space equipped with a multiplication, then we can see that this add x indeed a derivation. Okay. So this is just the second part, a times delta b, and then this is delta a times b. So which is delta act on ab. Okay. So this is the best way of remembering the Jacobi identity, that add x is a derivation. So now let us see some examples actually arise from these associative algebras. So they are the most important examples. So before that, let us first actually recall the important object of this course, which is GLN of C. So first we will recall the vector space M1 of C. So what is M1 of C? M1 of C, we by M1 of C, what we mean, it is the set of all n by n matrices over C. So this is the set of all n by n matrices over C. Okay. So now what one can do, so we can take this as a vector space, and one knows that this is indeed a C associative algebra. Okay. So because this M1 of C has a addition of matrices and multiplication of matrices, and we also have a scalar multiplication of matrices. So these operations make this M1 of C as a associative C algebra. So we will come to the definition of general definition of associative algebra in a minute. But before that, we can see that the following Lie bracket, the bracket A comma B, which is given by AB minus BA, which is called the commutator bracket. So which is called commutator bracket, and this makes this M1 of C as a Lie algebra. Okay. So this is a fact that M1 of C with this Lie bracket is a Lie algebra, and this Lie algebra is what is denoted by GLN of C. Okay. Since we are only working over complex numbers, we can actually drop mentioning C, and we often denote it by GLN C. We often use GLN to denote GLN of C. Okay, so now let us check actually this M1 of C is indeed a Lie algebra with respect to this bracket that we have defined. So it is easy to verify that this bracket is indeed a C bilinear map, because this is defined using the actual matrix multiplication on M1 of C, and we have taken the difference between them. So in each variable you can easily see that in variable A and in variable B, in both variables this is C linear map. So now we will actually check the skew symmetric, which is also immediate from the definition. So if we take the bracket A comma A, then this gives us that A square minus A square, which is 0. So it's immediate that the bracket A comma A is 0. Now only the non-trivial part is the Jacobi identity. So let us check that. So we will actually check the original definition of the Jacobi identity. So if we take the bracket x, y, z, so then we get x times yz minus zy minus yz minus zy times x. Okay, and this is true for all x, y, z in M1 of C. So now if we rewrite this, you can see that this gives xyz minus xzy minus yzx plus zyx, and this is what this xyz means. So now if you just compute other three elements, so I am just leaving it to see this. So now by permuting cyclically x, y, z, we can compute this y, zx, and then z, x, y. So then what we get exactly y, zx minus y, xz minus z, xy plus xzy. Similarly, here we get zxy minus zyx minus xyz plus yxz. So now you can see that so these terms exactly get cancelled when you add them. So if we just add them all these terms, so then you can see that this term corresponds to this, so they get cancelled, and then this xz y that is getting cancelled with this, and then this yzx actually getting cancelled with this, and then zyx actually getting cancelled with this. Similarly, this y xz is getting cancelled with this, and remainder zxy that is also getting cancelled with this. So if we add all these three together, then we are getting 0. So this proves the Jacobi identity. So that means this M1 of C with this Lie bracket is indeed a Lie algebra over complex numbers. So it is easy to see, okay, that the dimension of this Lie algebra is actually n square. So the dimension of this GLN is n square, and we also have a very nice basis called the standard basis of M1 of C. So we denote this Eij by the matrix which has on the ijth position 1, on rest of the entries are 0. So indeed, if we calculate the rth entry, then this is exactly 1 if ij is exactly equal to rs, or otherwise 0. So if we take this matrix Eij, so then that will form a, so this is a matrix n by n matrix, okay, with the entries rth entry is 1 if ij equal to rs, otherwise is 0. Then if we collect all this Eij running over 1 to n, so this will form a basis. So this will form a basis of GLNC. So this is very important basis, and one can also easily compute what happens between actually the elements of this basis. For example, the multiplication is easy to verify, so I will leave it as exercise. So if we take Eij and then let us say Ks, if we take Eij and Eks, so then you exactly get the Kronecker delta Jk Eis. So the Kronecker delta Ij is defined to be 1 if I equal to j, 0 otherwise. Okay, so this is the definition of Kronecker delta. It's a standard notation. So this is the definition of Kronecker delta. So now it's easy to verify. Whenever you take the multiplication of Eij Eks, then you get this delta Jk Eis. So now using this, one can easily calculate what happens if you take this Eij and then Ekl. So the bracket between them is nothing but delta Jk Eil minus delta Li Ekj. So this is what you get when you take the bracket between them. Now using this, one can actually explicitly determine the structure of this GLNC. So that will be done later. So now we will see more examples of this subalgebra of GLNC. So they are naturally defined Lie subalgebras. So most important subalgebra. So here are the more examples. So one can define what is called SLN. So SLN is what is called special linear Lie algebra. Special linear Lie algebra. So which is defined to be all the matrices in GLN such that the trace of X is 0. So, it is not hard to see that this SLNC is a Lie algebra on its own by taking the commutator bracket bracket A become equal to AB minus PA. So, I will leave it as exercise to verify that. So, here is the another important uh, family of Lie algebras, which is called SON. So, SON is collection of those matrices such that X transpose is given to be minus X. So, this is called special orthogonal Lie algebra. Special orthogonal Lie algebra. Okay, and with the same commutator Lie bracket, it becomes a Lie algebra. Indeed, it is a Lie subalgebra of GLNC. So, what is how one can verify? So, we need to verify that whenever we take xy in SLNC, sorry, SON, so the bracket xy also should be inside SON. For that purpose, we need to verify xy transpose is same as minus xy. So, let us check this. So, the bracket xy transpose is going to be xy minus yx transpose. So, which is going to be just xy transpose, because transpose is linear, xy transpose minus yx transpose, and AB transpose is B transpose S transpose. So, that will give you y transpose X transpose minus X transpose Y transpose. But Y transpose is same as minus Y transpose is minus Y, and X transpose is minus X. So, this gives us that minus Y times minus X minus of minus X times minus Y, which is exactly xy minus yx with the minus n outside. So, this is minus bracket xy. So, this proves that whenever we take the elements xy in SON, then the bracket xy transpose is also there, sorry, the bracket xy is also there. It is easy to see that SON is a subspace of GLN of C, and it is indeed Lie subalgebra or Lie, it is Lie algebra on its own. Okay. So, these are all some of the important examples that pop up in our course. So, mostly we will be actually focusing on GLNC and SLNC in this course. So, now let us see actually some other examples and definitions related to general theory of Lie algebras. So, one can actually take any vector space and make into a Lie algebra by defining the trivial Lie bracket. And if we take a Lie algebra G, and then that is said to be abelian, a Lie algebra G is said to be abelian if the bracket xy is 0 for all xy in G. So, basically G is a vector space defined with the trivial Lie bracket. So, that is what called abelian Lie algebra. Okay. So, I will make this very important remark. So, once we take this subalgebra of M1 of C, which is closed under this bracket operation, one can easily see that that will form a Lie algebra on its own by taking the commutator Lie bracket. Okay. So, if we take A, which is subspace of GLN, okay, let us say this is a subspace such that the bracket xy is in A for all xy in A. So, then I will leave it as exercise. One can check that A with respect to the restricted commutator bracket is indeed a Lie algebra. Okay. Suppose for example, if we start with A being already associative subalgebra, that means whenever xy in A implies the product xy is also A in A. So then it is easy to see that the commutator must be in A. Okay, but the converse need not be true. That Lie subalgebras may not always come from actually that associative subalgebras. But anyway, so if one actually starts with associative subalgebras, so if we start with associative subalgebra of GLN, then the condition that we actually have here is immediate. The bracket of xy is going to be inside A for all xy in A. So that means one can immediately think of the Lie algebra structure on this capital A. So that Lie algebra often is denoted by the bracket A. So this is the Lie algebra associated with capital A. That means the bracket is defined to be AB minus B. So now what the structure of Lie algebra tells us? So the structure of the Lie algebra tells us that how far this A is being away from commutative algebra. Okay. So the structure of Lie algebra bracket A tells us that how far A is being away from commutative. So in algebra, most of the time it is important to know like this information, how far actually this associative algebra is being away from commutative. Indeed, this Lie algebra gives us a tool to measure that actually. So the structure of Lie algebra. So there are many classes of Lie algebra one can actually define. So we will be defining that later. Solvable Lie algebras, nilpotent Lie algebras, and semi-simple Lie algebras, simple Lie algebras. So from these particular types, okay, if it is for example semi-simple, then definitely this Lie algebra is far away from being abelian. So that means the corresponding associative algebra is also like very much away from the commutative, being commutative. Okay, I will stop here. Thank you.